Our next presenters are Alicia Deal and Andrew Waite. Dr. Alicia Deal is a drinking water specialist with a master's and PhD in drinking water treatment. Starting in 1997, she worked for the TCEQ in various compliance and assistance roles. Since retiring in 2016, she has been a contractor on the Texas Optimization Program. Andrew Waite is a contractor for UTA, working at TCEQ in their Texas Optimization Program. Andy has worked for the EPA in the Drinking Water Section Administration Drinking Water Rules for 26 years. He administered the disinfection byproduct rule for Oklahoma until they obtained primacy and was a rule manager for the revised total coliform rule. Andy has also years of experience doing sanitary surveys and optimization work for states and tribes. Please welcome Alicia Deal and Andrew Waite.
This is what we're going to talk about, hopefully. What is nitrification? Who can it impact? And a little bit about the biology, about how it happens. We also want to talk about who needs to have a nitrification action plan and the different elements, the goals, baselines, what kind of monitoring you need to do, what kind of triggers you will have, and what kind of actions you will have when you actually notice something. Because it's one thing to be able to, it's like you have a fire alarm and it goes off and you say, okay, we've got a fire. Where? Okay, we know where it is. Okay, well, what do we do? Sometimes it's run away, but generally for those of us who are actually trying to work the system, trying to work in your water system, you're going to want to figure out how to go and actually fight that fire. You want to figure out how you're going to deal with the nitrification issue so that you can bring everything back to normal. Hopefully we'll put it all together so it makes some kind of sense at the end and you can actually have something that you can move forward with. Who needs to care? Public water systems who do chloranimation. And what is nitrification? Basically what it is, it's the end stage of a biological process where bacteria eat ammonia and then something eats those. It's a tertiary set of organisms that ends up in nitrification, and those taste and odor issues and the biological chemical issues with it. The problem is or the good news is it doesn't happen all at once. If you're adding chlorine, say, to your water and you're disinfecting, by golly, that happens pretty quick, right? If you're adding chloramines to your water, that acts fairly quickly. If you have nitrification, that is something that is developed over time. And the good news about that is that means there's time for you to test out in the distribution system to see what's going on and catch it, right, and address it before it becomes a conflagration. Right? You want to get that fire when it's a little bitty thing, when it's an ember. You don't want to wait until the entire house is on fire and then say, oh, look at there, that's a problem. You want to actually be able to deal with it when it's beginning. We'll talk a little bit more about nitrification as we move along. Why do we want to care? Because nitrification is in fact a risk. One of the things that you'll end up with, you will lose your disinfectant. All right, and so you won't have a residual, which is bad because then you can have other things that are going on, right? And we need to maintain that to maintain safe water throughout. But you also have the problem of persistent regrowth of bacteria in your distribution system, which can lead to some of those more acute things, right? Where you can end up with coliform positives and potential illnesses. We want to be bud nippers. We want to nip it in the bud. We don't want to wait until it gets all the way until it gets overblown. So who can have nitrification? Anybody who does chloranimation can have nitrification, including those who purchase water or redistribute water. If you have chloranimated water, by golly, you have that possibility of having chloranimation. If you think that you're using free chlorine, right, and that you're a free chlorine system, but you have ammonia in your water, you might be having issues too, okay? Because they can form chloramines if you already have nitrogen or ammonia in your water. Surface water treatment plants, and there's a lot of surface water treatment plants out there, and most of them do in fact chloranimate. There's a few of them that don't. Any system that uses has chloranimation. What are the things that you need to be able to do? There are some rules out there, and one of the things that we require a nitrification action plan. So you actually have a plan out there this is what we're going to do. It's kind of like the firefighters, right? They already have some idea of what they're going to do when they go out to fight a fire, right? It's not just like, oh, well, here, let's go, right? You want to make sure that that you actually have a plan. And to me, it's really important. It's going to have to be unique to your system. We can't just do a cookie cutter, boom, there it goes, boom, there it goes, boom, there it goes, because every system is different, you know? And the fact is one of the things that happens is, who's had growth in their water system where you've got more connections? Who's had fewer connections over time, or you have a area of maybe downtown that some of the businesses are closed, right? Where you have changing water use, right? A nitrification action plan is not a static thing. It's not something where you say, okay, I did it once. I did it back in 2000, right? So I've got that plan. It's good, right? You're going to have to keep looking at it as your water system changes, as you keep developing things in your distribution system. You're going to want to make sure that you keep your nitrification action plan up to date so that, in fact, you want to be able to find the issues again before they get bad. You want to make sure that you can do that, because you don't want to end up with, and they call it a bloom, where you have a whole bunch of nitrifying bacteria in your distribution system, because then you've got to go through a lot of effort to address it. Okay, here's a shorter answer of what is nitrification: a biological process in which ammonia oxidizing bacteria eats ammonia and makes nitrite. And then, as nitrite increases, then you get another, this is the tertiary organisms, the nitrite oxidizing bacteria, NOBs, eat the nitrite and make nitrate. And this nitrate is that end product. That's kind of, in some circles, they call it a fatal daughter. In the process, monochloramines is destroyed, which is a bad thing, because in fact, you want to make sure that you do in fact have a residual in your distribution system for all kinds of reasons, not the least of which is protecting public health. And there's rules out there saying that you're supposed to. But the real thing is you want to make sure that you're protecting public health. Rules are just out there to get those people who aren't dedicated, who aren't really going after making sure that they're producing the best water they can. The rules are out there for them. For the rest of it's because we know that we want to protect public health, because that's the area that we're in. We're in public health service. That's what we're trying to do. The normal chloramine reaction is, we want it to be in the monochloramine zone. If you were here for the earlier presentation, you know that's in that first part of the upswing, somewhere probably about a ratio of somewhere between 1 to 4 to 1 to 5. You don't want to be too close to the 1 to 5, because that's kind of a teetery edge, and I'm not going to talk about that anymore.
So here's the thing. You know, one of the things that we didn't get to in the last chloramine presentation, does your ammonia go up or down in distribution? It goes up. At your higher water age, which is already where you're going to have a lower residual, you're going to have an increase in ammonia, partly because of this equilibrium. There's always that little bit of ammonia forming. And then because of this, the ammonia is formed. Chloramines are actually strong chemicals. Anytime you've got a chlorine around, that's an attack chemical, right? And so monochloramine is attacking pathogens, it's attacking biofilm, it's also attacking each other. So we have the two monochloramines up here, and they attack each other, and when they react, they go to ammonia. And so you get some ammonia in there. Well, you know, that nitrification action is started, the biological action is started by having ammonia present for those AOBs, ammonia oxidizing bacteria, ammonia eating bacteria. If that ammonia is there on the front, there's a little bit of dissolved oxygen in there, so ammonia plus oxygen, that ammonia oxidizing bacteria takes it and makes the nitrite with an I, NO2, plus a little hydrogen ion, 3 hydrogen ions in there, and some electrons, which we're going to ignore because we don't have an electron meter. And so that ammonia, having that food there for those guys to start eating, is the whole crux of the matter. And so we get nitrite. Now we get those nitrite-eating bugs, right? nitrite with an I, they take a little bit of oxygen from the water and they slam another oxygen onto that poor little N that's just getting, slammed every different way. And now they get nitrate with an A, NO3 minus, with that additional oxygen on there. So that's our whole process. So let's look at it. I'm a visual person. I like pictures. So here we have this bacteria. He's got a little flagell on there, just like a regular old bacteria, kind of like our total coliform, but a little different. So AOB, ammonia-eating bacteria, AOB, eat that ammonia, produce that nitrite, and then the next step, well, now that we have food for them, the nitrite oxidizing bacteria can eat that nitrite and make nitrate with an A. Real quick here, Destiny Gephardt told me her 10th grade teacher told her how to figure out nitrite and nitrate, and it's nitrite with an I has 2 oxygens on it because it's on a diet with an I. Nitrate with an A has 3 oxygens on it because it ate all the oxygen. And I'll tell you what, when I'm doing this presentation, sometimes I'll say them backwards. I'll try not to. So nitrification in the environment, it happens in the environment. It also happens in wastewater treatment plants. And in a certain kind of wastewater treatment plants you probably learned about, even if you're not operating one when you took the wastewater stuff. So in the environment, we have our happy little fish and our happy little plants. And so it's gonna have some ammonia there because we may have a little bit of effluent or runoff coming in there. The limits in wastewater for ammonia are very tight now, but you could still have runoff. You can still have fish, they're normal organisms. They're gonna have some excreta that contains ammonia, and then some plant remnants. But in the environment, so those nitrosomonas or ammonia oxidizing bacteria eat that ammonia, produce nitrite, and then the nitrobacter, the nitrite oxidizing bacteria, eat the nitrite and form nitrate. But here's the thing about the natural environment. We've got all this other stuff going on biologically, right? You've got that silt in the bottom of the river or stream where these little organisms that don't need oxygen live, and they can actually transform that nitrate into ammonia and stuff and feed back to the plants and animals. So we have a whole cycle, so it's balanced. Unless you get out there and it's looking terrible, that might not be balanced. But in a beautiful stream, it's balanced. In a pipe, though, it's different than the stream. First of all, there's no happy little fish or plants or something's worse going on than we even thought, right? But we do have a biofilm. In every pipe, you're going to have at least a tiny layer of bacteria sticking to that pipe. They love to stick to stuff. And we're going to have some ammonia. We might have naturally occurring ammonia. We do have decomposition of chloramines, but we also added some, so we could have some left over from that process. So with the ammonia, we jumpstart that nitrification process, right? And it goes forward in the biofilm, right? So those same bacteria, you get one little seed bacteria in there somehow, and we can start that process. Now, problem is, with that, there's a loss of residual. The analogy I use for this one that I need to put in here is like, you go out and you're gonna get a hamburger, and what you want is that juicy hamburger patty, and you're just gonna eat that, it's gonna be so good. Well, they put some lettuce on there, and they put some ketchup and mustard, and you don't really care about that stuff, but you go ahead and eat the hamburger and the lettuce and stuff anyway, right? Well, for these bugs, they like to eat ammonia and then nitrite, but that's the hamburger for them. And so the residual, the chlorine, is kind of like the lettuce. They're going to eat it anyway, but it's a side effect. It's co-metabolism for the long word. So we want to find these bugs, but we're not going to necessarily look for actual bugs, right? We're not going to do some kind of where's my bacteria test. We want to find that nitrification somehow. So we need to talk about what it makes the water look like. we can keep track of nitrification by measuring total chlorine, monochloramine, and ammonia, right? We already talked about those in the last presentation, but also nitrite, right? The food for the second set of bugs, and nitrate, what the nitrite oxidizing bacteria make. So that's why that nitrite and nitrate monitoring becomes important. And abnormal levels of these chemicals might tell us we've got nitrification. So in normal conditions, as water age increases, we see that total chlorine, it's going to decay, right? It's going to go down. And monochloramine residual is going to track pretty close generally. Again, Jack talked about this yesterday in his water age presentation. They're going to track, and the monochloramine's going to do what? It's going to go down. It's working, man. It's killing pathogens. It's killing biofilm bugs. Down. Ammonia, what we just learned from Andy, is going to go up because that happens with that decay chemistry, right? Now, what's going to happen to nitrite? Let's see. So normal conditions, we don't have nitrification going on, right? So the nitrite should stay the exact same. There's nothing going on chemically in normal conditions when everything's going right that would change the nitrite concentration. Nitrate, same answer. No biology, no change in nitrate. Okay? So here's what it looks like. We've got the various residuals on the y-axis, and then we've got water age across the x-axis. So when we first get in there, we're at about a 3.5 of total, and mono is almost the same. Those things drop down as we get to higher water age later in the system. And we see the red line, which is ammonia, we see that go up, right? That's what we just said. Nitrate, nitrite, no biology, stay the same. But let's look at nitrification. So as we have nitrification, first of all, what's our first indicator of this? When we're seeing that total chlorine drop on us, because that's what we're looking at the most, right? And so we're used to seeing a 2 out here, and we're seeing a 1. Now we're a little bit worried. Monochloramine also is going to go down farther. Free available ammonia, what's going to happen to this? When we had normal conditions, it was going up. It was released from the chemistry. Now we throw those nitrifiers in there, and that ammonia starts going down because somebody's eating it. And now what does nitrite do? Nitrite with an I. Remember, because when you eat the ammonia as a bug, you're producing some nitrite. So initially, we're going to see that go up, right? But then when, sorry about the lines and stuff, then when the next set of guys, the NOB, the nitrite oxidizing bacteria, start eating it, that nitrite is going to go down as those nitrite oxidizing bacteria eat it. Nitrite goes down, nitrate goes up, okay, when nitrification is really bad. And so what that looks like on the same kind of picture is, first of all, we start at the same point. We're starting at about a 3.5 on the total and mono residual, right? But by the time we've gotten a little ways down that system, we're already losing more total chlorine than we would like to see gone, right? And at the end of that system, at the high water age, it's really bad. What happens to the ammonia? Well, with high water age, instead of seeing increasing ammonia, we're seeing less ammonia in there. So that's our first clue. Where would our ammonia go? There's only really one place that our ammonia is going to disappear to, and that's nitrification, okay? What about the nitrite? Well, we see already, first of all, that it's not the same all the time. And so we go down to the first average water age and we see, oh, it's increasing. And we go down all the way to the high water age, and now it's decreasing again. Well, that's because we see that nitrate, as soon as the bugs have some nitrite to eat, they start eating the nitrite and producing nitrate, which will cause that nitrate to be higher at your high water age sites. Now, I'll grant you, nitrification is not the only thing that can wreck your total chlorine, okay? So we'll talk about some clues that when you follow up on a bad total chlorine reading, might tell you, oh, never mind, this is not nitrification. First of all, if you're near the plant, because you got to be near the plant for this, you could be in that unstable zone and things could be going bad on you. So maybe your demand dropped, instead of having a 5-to-1 ratio on the break point at the tippy top, maybe something happened to tip you over into the unstable zone and you're losing residual because of that near the plant. Another thing that can happen is if you've got a little bit of backflow. One of the things we've got to remember, this mysterious distribution system is impacted by pressure all the time. Every time you turn a valve, you've got the opportunity for what we call a pressure transient, which is just basically saying, and another thing Jack said is flow is not continuous throughout the whole profile of a pipe. It's more in the middle and less on the edges. So you've got that potential to suck things in through a small crack that you haven't detected and fixed yet. And so you can get intrusion, I for drinking water, right? It's not as bad as for wastewater, but you can get a little intrusion of dirt from the surrounding soil, or you can have a straight up cross connection with some pollutant that causes an increase in demand in that water pipe. When that happens, it's going to affect your total. It's going to use up some of your chlorine that doesn't usually get used up, but it's not a biological process. So if we look at the clues, if we have a loss of chloramine, maybe we've got nitrification. If we have a disappearance of ammonia, oh yeah, maybe we've got nitrification. That's a red flag. If we see that nitrite, and this is most valuable for those of you who are running SL1000s and running nitrite in your routine sampling, many of you are probably sending nitrite out to the lab, so you don't see nitrite and nitrate as frequently as those who have that instrument. But you can always go back out there when you've got a loss of chloramine. You can go back out there and test your nitrite and nitrate and see if that nitrite is going down or up, or if the nitrate is going up. Now, we have a pH decrease in some waters. Some of y'all are from East Texas. What do you got? You got low alkalinity, right? And you put just a little bit of acid in that water and boom, you got a pH change. So you can see that. If you're out in West Texas, you got a lot of more calcium and stuff in there. It might be a little harder to change the pH of this water. You might not see nitrification in a pH change, but it's something to look for. Biological clues, the real pain in the neck is we've seen, like when we first started doing the revised total coliform rule, I did a bunch of level 2 assessments, and about 40% of those, we were out there because there were just total coliform pops over and over again, right? And 40% of those were due to nitrification allowing regrowth of coliform organisms in the distribution, and not popping any E. coli, not popping those bad boys, but popping a lot of total coliform. Now, if you happen to do the good old heterotrophic plate counts that we used to do, you'd see it there real well. Or if you had the polymerase chain reaction going, you can actually count those bacteria. So I say, I'm old, all y'all are young and good looking, and in 20 years, you're gonna be able to take your phone, dip it in the water, and it's gonna say, oh, you have 4,967 nitrifying organisms in your water. So summing up on that, it may be nitrification if your total and mono are too low, and your nitrite is higher than normal, or if it's gone really bad, lower, and nitrate is forming and going up. It may be unstable chlorine if you're really seeing things variable and your mono and your total are really splitting apart. Like usually your mono is like close to your total and now it's really far away. And of course in the breakpoint curve, in that middle thing where the line is going down, you got your unstable stuff there. And so you're not going to have any, that's when the fights break out in the chloramine bar, right? And so you won't have any ammonia. But that is a chemical reaction, not a biological reaction, and so it will not impact the level of nitrite and nitrate. Increased demand, again, you see that drop in mono and total, but you don't see any change in ammonia, nitrite, or nitrate because you don't have those bugs going on when you're just sucking in some mud out of that surrounding soil or you have an actual cross connection. So the nitrification action plan is what TCEQ put in place to try and help, but it's kind of like a plan for monitoring, just like we try and figure out if there's bacteria in the water by measuring total coliform. We try and figure out if there's nitrification happening in the water by having a nitrification action plan. And there's kind of 5 pieces, a map with your sites, sample schedules, list of methods, and then we'll talk here about these goals and baselines, triggers, and actions to take if you see nitrification. And then, of course, it's good to have roles and responsibilities. So goals and baselines. Now, this is kind of where there's some action. You have to do something to set up your nitrification action plan for the first time when you're like, oh my gosh, I've got this data. What does it mean? What is it telling me to do? We have to figure out what normal is. We have to define that normal. And often you've got your total chlorine information, and by this time, since this all started in about 2004, 7, 15, the rule went in, we're looking for triggers that say it's not normal. So you've got to have some initial data, right? You've got to have some good data set to look at to be able to say what's normal, what's not normal. So we're going to have to set triggers based on that data. So we use mapping and graphing to figure this out. For a single result won't tell us anything. I got a 3. Well, it tells me I've got 3 milligrams per liter. I'm pretty happy, but it doesn't necessarily tell me that if I should have a 4 at the, say, entry point to the distribution system. So we compare the results to see the connections between them. If we compare the data from one site over time, it's going to be trending analysis, and we can see maybe differences between summer and winter. If we throw that map out and kind of take a snapshot and say, okay, today, August 7th, 2025, we have these numbers throughout our city today, or system of any kind. So it's a snapshot. It's a one-time snapshot. Now we can compare multiple snapshots, and that would be a combination of trending and mapping. We would love it if we went out there and normal was like the same every time. But honestly, with our methods, we could take one sample of water, one aliquot of water, one analyst, one instrument, and take multiple readings over time. And there'd be a little bit of variability, right? But that's okay as long as it's with a narrow band, right? And so we're going to start our analysis of setting goals and baselines, our normal levels. Say, okay, we're going to take an average. That's kind of what our normal is there. So here we have our little normal range. We want to put limits on that. We want to have a range where, okay, inside of here it's okay, but when we get outside of this little range, we're a little worried. We need to do something. We could be in trouble. And that's our yellow flag triggers, right? That's our, gee, better follow up. Hope it's nothing, might be nothing, but let's check. Now, sometimes stuff happens and it's just like, holy cats, how did I get this number? And I need to act right away to respond to this strange, way off spec number and make sure that I can control the quality of my water. Just kind of like we use the analogy of a stoplight. So we looked at normal conditions, and normal conditions are different throughout the system, right? It's like what you have coming into the system, best you're ever going to get, and what you have at the far reaches, farmhouse, 4 miles outside of town. The normal is going to be different for those places. So here, let's look at good old Second Avenue here, kind of average-ish water age. Instead of always wanting a 3.5 here, we'd be happy if we've always got a 3, right? Because we've already decayed a little bit. So let's set some goals for Second Avenue, for this average water age. First thing, we'll just do total, but we need to gather a bunch of data so that we can look at all of it together. So that would be our initial data set to use for this exercise. So just looking at all of these things, we see there's a little variability, but do you think nitrification was occurring during this data set, during this time period? No, man, it looks really, really pretty darn good. Probably better than things usually look because I made it up. And so we're like, okay, well, this is a good data set for setting normal levels because nothing weird is happening during this time period. So we're going to look at just total. We'll take all of those results from that 3-month period, run an average, and we're going to say, okay, our average was 2.81. We might want to round that to 2.8 because we don't need to have that confusion. Throw that on the graph and say, okay, do I like that? Yeah, normal looks normal in there, right? And so now we're ready to set triggers, and this is a little bit trickier, especially when you're first coming at this, right? So setting triggers, we're going to use that same data set, and we want to first have the yellow ones, the gosh, I'm going to follow up with an action, but I'm not necessarily going to call my boss freaking out, help. So they're somewhat off spec, and then we'll set those red flag triggers where, okay, I need to call my boss or do something. So talk about first, you need the upper and lower triggers. Now, total chlorine and monochloramine, obviously that's our number one thing that we're looking at. That's where we're looking at how we are doing on killing pathogens and knocking out biofilm. So we definitely need a lower limit. We need a lower limit for every water system. And that lower limit, do you think it should be 0.5 anywhere? Probably not, because if you come in at aiming for 0.5, there's going to be a time when you slip a bit and you get 0.4, and that's not a good number. If you're dosing, you definitely want an upper limit as well, because you don't want to waste money on chemicals, right? You want to just put the chemicals you need to put in and not over-chemicalize it, right? And even for purchased water, you may want to be ready to call your supplier and let them know, hey, dudes, you're giving me 0.45 milligrams per liter of ammonia. That seems like, is something happening up there? For ammonia, for me, that lower ammonia limit, like when my ammonia starts dropping off of what I'm used to seeing, I'm a little worried. I'm worried that some ammonia-eating bacteria is chomping that stuff down, right? And so we need a lower limit. We kind of need an upper limit, just like that purchased water system that the supplier was sending us 0.45 milligrams per liter of ammonia. That's a lot of bug food, right? So if we can knock that down a little through conversations or in an actual treating system through managing our treatment, that'd be a good thing. We don't want to feed the bugs, for heaven's sake. For nitrite, we're going to need an upper limit, right, for incipient nitrification, and a lower limit maybe to tell us, oh my gosh, has this stuff started turning into nitrate? Nitrate is the hardest to monitor, and it's the one that is least useful for most water systems on a day-to-day basis, but it's something where you definitely want to know if it's going real high, okay? So here's our data set again, or that data from that 3 months of monitoring that set our initial baselines. That we might do that periodically every year or two. So we have the average, right? We set that as normal, right? That's our normal. So let's set a lower limit for total coliform here. What we're going to do is we're going to get our nephew who's really good at Excel, to calculate the standard deviation in the Excel spreadsheet, because it's real simple, and say, okay, that tells us kind of how things vary, the standard deviation. We'll subtract one standard deviation for this initial run and call that our yellow flag, subtract 2 and call that our red flag. So again, just looking at total coliform triggers, here's our normal, here's our yellow flag lower trigger for total chlorine, and here's our red flag. So let me ask you, how many times did somebody have to go out and do something before, during this 3-month period? So only one time in 3 months, and so that's not too bad. Now, let's say we trigger that. What actions are we going to take? I think that the point is all of this is going to overlap. Every day in your system, you are taking preventive actions to ensure that your system runs right. You're just going to do a little more of it when you hit one of these triggers. And even more when you hit a red flag, and maybe something different when you hit a red flag. So the first step is always verify those results. You might want to take another sample yourself, have your buddy take it, use a different instrument, but verify your results before you freak out, okay? Because it may be that you got a bad powder packet, a bad chem key. If you got an SL1000, you may have a tray going bad. Find out. Now, the next part is figuring out, is this because of something going on in the houses in that area or the buildings in that area, or is it in fact gotten throughout that system? So you check the next door, and see, is this system-wide in which you need to go back upstream to the source? But you know, I'll tell you, a lot of times it's just a valve that should have been on that's off, okay, and that's what's killing you. So do a valve sweep in the area and do sampling in the area. And only then do any flushing, okay? Find out where it's at. Find out where the nearest good water is and flush from the good water, push that bad water out. But know where you've got good water before you do that. Now, unfortunately for red flags, the temporary conversion to free chlorine is our best tool, but we're not talking about that today. And in fact, we're going to shoot through this. We have all these other parts of the nitrification action plan, and we've provided this kind of matrix to summarize your goals, baselines, and triggers. So just real quick, when we first started this rule, a lot of people would print our example off the web and put it in their nitrification action plan, and don't do that, okay? Put your own sites, list your own sites, your own goals, your own triggers. We have examples of that, you know, verify results, those actions. You can use those or modify them, but try and follow them when you trigger. You know, final take-home message, it's a living document. It should be changed as conditions change. Just like Andy said, there's communities, you know, if you're a community near Austin or Dallas or Amarillo, you may be growing pretty fast. If you're somewhere else, you might be shrinking. You might be switching up who's in charge of which chunk of water lines. Change it when things change. Chloramines, they can be our friend, right? But we need to stay on top of them and avoid, we avoid the disinfection byproducts. They last a long time, but we gotta stay on top of nitrification. Thank you so much for your attention. I appreciate it.